Okay, hi everyone. Welcome to the last Martin Center Research Seminar of the Michaelmas term 2020. This seminar is hosted and supported by the Martin Center for Architectural and Urban Studies at University of Cambridge. Today, we are very happy to invite Dr. Jason Palmer, the Director of Cambridge Architectural Research and Cambridge Energy. Jason has worked for 22 years researching energy use, energy efficiency, and carbon emissions from buildings. His presentation today will cover the opportunities and challenges brought by electric heating in the UK in meeting its climate change targets. Welcome, Jason. Thank you for coming today. And also joining us on the panel today are Dr. Helen Mulligan, also one of the directors of Cambridge Architectural Research. Her expertise is on climate responsive design. And we are having Dr. Ying Jing, the director of Martin Center. Hi, Helen and Ying. Thank you for coming. I'm Kai, one of the conveners of this year's seminar series. Now, my colleague Nacha will explain how to interact with our speakers on Zoom. Nacha.
Okay, thanks Kai for the introduction. So just a quick housekeeping before we start is the talk is going to be about 35 minutes and then we will open up the floor to questions. So the seminar today is being live streaming on Facebook as we speak up until the end of the presentation. What this means is that the discussion that follows the presentation will not go online. There are several options for you to join in the discussion. You can either type in your questions in the Q&A box, or you can virtually raise your hands, which would allow you to join the panel. In doing this, you'll be able to turn on your audio and video and talk to the speaker directly. So this is much more interactive as an option. And so if you could do this, it would be very much preferred. And before I hand over to Helen, I just have a few things to add, and I promise I will be very brief. So we know that some of you will have to leave at 4 p.m. on the dot. So I would like to use this opportunity to get some of the important messages across before we lose you at 4 p.m. So this is the last seminar this year, and we'll be back again on the 27th of January. This will be on Wednesday and at 3 p.m. as usual. We've got an amazing lineup for the next term, and the term card will be circulated shortly. So what I can tell you now is that the first speaker in the new year will be Phil Stedman, who was one of the earliest member of the Martin Center himself. So do save the date, and I look forward to seeing many of you there on the 27th of January. And the second thing is that on behalf of the convener team, we would like to thank all the speakers and all the chairs, so including Jason and Helen today, of course, for their time and for sharing with us their amazing research from different perspectives in architecture. And of course, thanks to all the attendees. Without your support and your attendance, this whole seminar series wouldn't have been possible. And finally, I would like to thank Ying, director of the Martin Center, for his amazing support and for trusting us, for being such a supportive teacher, a colleague, and a friend. So without further ado, I would like to hand over to Helen. So the floor is yours, Helen.
Thank you very much, Nadja. I'm Helen Mulligan. As Kai already mentioned, I'm a director of Cambridge Architectural Research. Jason has been one of my co-directors since 2003, and he has a deep knowledge of energy modelling and policy guidance, developed notably through more than 30 projects with the Department for Business, Energy and Industrial Strategy for the UK, that's BEIS. But he's also worked in the Martin Center with Professor Robin Spence and Sebastian Macmillan. Now, Jason's work in this area developed and kicked off on a national scale, working for the Scottish government on a model of the Scottish housing stock and forecasting emissions from it through to 2050. This was noticed by BEIS, who subsequently contracted Jason and Car's team to carry out modelling based on the Cambridge housing model for the entire UK. This has culminated in reports up to 2014, and Jason has been able to contribute to national statistics on energy use. Besides that, he's also coordinated data collection from the building performance evaluation study of many types of buildings within the housing stock, within the building stock, but also particularly for housing, with the looking at the cost of retrofitting houses and barriers to the uptake of energy retrofit in social housing. Now he's turned his attention to electricity as a source of heating within the domestic building stock. So not only does he have a great familiarity with modelling, but also a huge amount of data to bring to the question of the day. Will electric heating allow the UK to meet its climate change targets? As mentioned before, I'm afraid I'm going to have to leave quite promptly at 4, so I'm going to thank Jason in advance for what I'm sure is going to be a very interesting talk and followed by a stimulating discussion. Thank you, Jason.
Thank you, Helen. And thank you for that flattering introduction. Thank you, everybody, for joining this afternoon. As you will have surmised from Helen's introduction, I'm not an architect, so I can't promise this afternoon to show you beautiful buildings, but what I think I can promise to do is to give you a presentation that is quite distinct from the others in this seminar series. One of the things I've particularly enjoyed about this series so far have been the historic references to the ancient Chinese trade routes, to Roman roads, pre and post-colonial Pakistan. I'm going to extend this now into the future by telling you a little bit about the work we've been doing on this model we've built for bays. That's the part of the UK government that is responsible for energy and climate change. But before I go on to talk about the model, I want to thank the whole team that's been involved in this work, and especially Nicola Terry. Without Nicola's commitment and modelling skills, we would never have been able to achieve what we have on this project. To give you a feel for where I'm going to spend a little bit of time putting the work into context, talking about the government's objectives in this area. I'm going to describe the house types or archetypes that we've defined to be representative of the 27 million homes in the UK. I'm going to talk a bit about the model itself and how we validated it. Then I'm going to describe some optimization work we've done using the model, and finally to draw out some conclusions. Okay, let's kick off then about the context. Heat accounts for more than 1/3 of overall carbon emissions in the UK, and of that, around 80% comes from housing. What this means is that it would be impossible to meet the UK's legally binding commitments on climate change to achieve net zero carbon by 2050 without doing something about heat. Historically, what we've done on heating is to try to enact energy efficiency improvements on homes. But the bad news is that the pace of those energy efficiency improvements has slowed quite dramatically in the past 10 years or so. And that's for 2 reasons. Firstly, because we've already picked the low-hanging fruit. So now the low cost and the easier interventions that make homes more efficient have already been done in most cases. The second point, though, is a change of stance by the government, which means that the private sector, the market, is expected to do more work in this area. And the government has withdrawn somewhat from funding energy efficiency improvements in homes. Now, though, the government is pushing electrification of heating as a way to reduce emissions. And you may have noticed the Prime Minister's announcement 2 weeks ago that we have a new target to install 600,000 heat pumps a year, every year, by 2028. So a very, very dramatic transformation in the way most homes are being heated. And the reason this is a good thing, and the reason it supports our climate change objectives, is because carbon emissions from electricity have fallen markedly. They've fallen by more than half over the past 12 years, from 550 grams per kilowatt hour 12 years ago down to about 230 grams a unit today. And that trajectory of falling emissions per unit of electricity is likely to continue falling into the future. The problem is, though, when it comes to electrifying homes, there are significant barriers. Firstly, most householders are accustomed to gas heating. They're quite happy with the service they're getting from gas, about how easy they are to control. They understand how the system works, and they are reluctant to embark on a disruptive program of work in their homes that means changing away from gas towards electricity. The second one is the cost, and the cost one bites twice. Firstly, because capital costs of switching over to electric heating are high, significantly higher in most cases than simply buying a new gas boiler. And secondly, because the running costs of electric heating are quite significantly higher than they are for gas. And per unit, you would reckon I'm paying 3 or 4 times more per unit of electricity than we currently do for gas. Just to bring home this point about the pace of change slowing over recent years and the rate of energy efficiency improvements becoming delayed recently, this chart shows all homes across the UK divided into the EPC bands from A to G. And while we have been successful in moving millions of homes, a small number of millions of homes, from E up to D, rating D to C, so significantly better improvement for those homes, we are still, after 40 or 50 years of work trying to improve energy efficiency of homes, left with the residual 70% of homes that are still EPC level D or below. And these homes are sticky. They're hard to move between these EPC bands. And this is significant when it comes to electric heating, and particularly heat pumps, because the conventional wisdom is that you need to have an energy efficient envelope to start with before you go ahead and install electric heating. And ideally, you need an EPC band A or B, which is to say a house that has insulated floor, walls, loft, and high performance windows before you invest in a heat pump. How do we fit into all this? Well, we won a competitive tender exercise that BEIS ran at the beginning of this year to develop a full dynamic simulation of UK homes that would tell the government how they can implement electric heating at lowest cost. So how they can overcome that significant barrier to electric heating, which is the fact that the costs are so high. We're giving you a sneak preview of this work. I'm giving a sneak preview of this work now, and we're due to complete the work in February next year. I'm going to talk you through stage by stage a simplified chronology of the work that we've carried out so far, starting out with house types or archetypes that we developed to represent all homes in the UK. And we did this in 2 stages. First of all, we looked very hard at form factors. That's to say the ratio of wall areas to floor areas, wall areas to window areas, and the footprints of individual homes. And we tried to divide all homes up into a limited number of forms. And these forms are relatively immutable. They would be difficult to change the forms of homes. I would contrast this with aspects of homes where the performance can be changed, like installing additional insulation or by changing the windows. So after we divided into a relatively small number of homes based on form factors, we came up with 6 form factors, which were sufficiently generic to cover the stock. We then looked in more detail at the construction types, and particularly the floor construction, whether they had solid or suspended timber floors, which make quite a big difference to thermal performance. And we looked at the walls and the contrast between cavity walls and solid walls. Cavity walls relatively easy to insulate. In most cases, they have already been insulated, whereas solid walls in most cases have no insulation and are more expensive and more difficult to treat. And we did all this using the English Housing Survey data, which is pretty much the best description we have currently of English and UK homes. And what came out of that process, those archetypes, were these 12 archetypes that describe collectively 82% of the stock. You can see the archetypes for yourselves, starting with flats. We have 4 types of flats: bungalows, terraces, moving on to detached homes. And you can see the TFA column there, the column 4 in this table, shows you how the floor areas vary between these archetypes. So that they are contrasting types. And what I would invite you to do is to consider your own home and how your own home fits into this this set of archetypes. And I think it will make the rest of the the presentation more interesting to you if you have in mind your own home and how these costs that I'm going to present relate to where you live yourself. These images here, they're not precisely the modelled homes that we have, but they've asked us to try to find representative images so that people can kind of make a more tangible description of the house types that we're modelling. And again, I wouldn't expect a perfect match between your own home and these images, but you should be able to find one that is a pretty good match with your own home. Okay, regarding the modelling, I don't have time to describe the models in enormous detail now, but I will pull out a few key features. In each case, we devised a floor plan for those 12 archetypes, and all 12 were modelled initially with a base case heating system, which was either a system boiler with a hot water tank, a combi boiler, or storage heaters. We went on to model 7 alternative heating systems, and these 7 heating systems could be put together with each of the 12 archetypes. And the 7 heating systems we modeled, these are all electric, all upgraded heating systems, are low and high temperature air source heat pumps, low and high temperature ground source heat pumps, reversible air-to-air heat pumps, a little bit like the air conditioning systems you see in some hotels, a hybrid heat pump, which is where an air source heat pump is linked with an existing gas boiler, and both are used in tandem, and finally radiant electric panels. So all of these heating systems were linked up with the house type archetypes. And on top of that, another layer of permutations was whether these heating systems were used with or without time of use electricity tariffs. Now, time of use electricity tariffs are where you pay a variable rate depending at what time of day you're using electricity. So in peak demand periods, typically between 4 and 7 p.m, you would expect to pay 2 or maybe 3 times more per kilowatt hour of electricity, whereas in off-peak periods, overnight, when there's low demands for electricity across the grid, you would pay significantly less. There's a big contrast between that and the arrangement we have currently for most homes, which is you pay a flat rate, the same rate per unit of electricity, regardless of when you're using the power. We also modelled all of these heating systems with or without batteries, thermal stores, and oversized radiators or underfloor heating. And the oversized radiators and underfloor heating are important for electric heating and heat pumps because oversized radiators or larger heat emitting areas in tandem with insulation allow lower flow temperatures to be used in the heat pumps. And lower flow temperature for a heat pump means greater efficiency, improved coefficient of performance. This is a schematic for just one of the heating systems, as it was applied in the models. It's a simplified version. This is the low temperature air source heat pump, where water is being distributed at 45 degrees C to radiators, and it's providing some of the domestic hot water load, the DHW load there, topped up using an immersion heater. And the immersion heater and water heating generally was an important consideration in our modelling, particularly to do with Legionella, because one of the disadvantages of heat pumps in providing hot water is that they struggle typically to achieve a 60 degrees C temperature in the hot water cylinder, which means you incur a Legionella risk. And 45 degrees is not sufficient to be killing Legionella bacteria, and there's a risk of Legionella building up and potentially causing long-term health issues. So what we did in the models was to implement a Legionella cycle whereby water is heated to 60 degrees for a 2-hour period every weekend. It's an off-peak period, and that reduces the risk or eliminates the risk of Legionella disease in heat pumps. As well as the heating systems, we also implemented in models a whole series of fabric measures. There were some low-cost measures like airtightness or top-up loft insulation, where you add on a little bit more loft insulation than is installed initially. And there are expensive measures like triple glazing or floor insulation. And all these things are linked in complex ways geometrically. So if you can imagine a multi-dimensional matrix, so that there are lots and lots of different permutations of measures, tariffs, and configurations for each archetype. And in fact, we worked out that there are between 12,000 and 100,000 different combinations of measures that could be applied for each of those 12 archetypes. The next stage in the analysis was to validate our model. A model that hasn't been validated or is of little value. And we did a number of steps in model validation. We compared against a commercial piece of modeling software called IES, very widely used in the UK for dynamic simulations. And that gave a pretty consistent estimate between energy consumptions and internal temperatures to our models. And we also looked hard at coefficients of performance. And these coefficients of performance are a critical measure for heat pumps, a really important measure of how many units of thermal energy heating you get out for every unit of electricity that goes into a heat pump. This is a really important concern, which we sought to validate for all of the heat pump systems. We struggled, though, when it came to air-to-air heat pumps because they are very seldom used in housing in the UK. So we looked at Finland and we found good data on Finnish air-to-air heat pumps, and we compared the coefficients of performance we were getting from our model with those from the Finnish data. And again, we found consistent curves. We did similar things using data from Mitsubishi and Panasonic for the more common forms of heat pumps. Turning to optimization, this is a complex art, and I'm not going to go into incredible detail now, but I will say that we used a genetic algorithm which runs iteratively over many occasions, making small changes and repeating successful changes in the model where changes result in reduced costs. Our task was to come up with the cost optimal set of upgrades and heating systems, and this is what the optimization set out to achieve. And the chart you can see has each dot as a model run, where red points on the chart are the cost optimal selections of packages, which are on the so-called Pareto frontier. They're the optimized, the cost optimal frontier. Okay, returning to the house types and hopefully the choice of archetype that you've made yourselves, I'm going to explain how the optimization process resulted into packages of measures and particularly heating systems now for each of the 12 archetypes. The first two flats, these are the flats that started out with electric storage heaters as heating systems, continued with storage heaters as the most cost-effective way of switching over to electric heating. The difference is, though, they're not traditional old-style storage heaters. These are new high heat retention storage heaters, which include fans and much better control than we experienced in the past. The next four house types, so that's the other two flats, the medium end terrace with solid walls, and the sprawling detached home, also with solid walls, both were upgraded with air-to-air heat pumps, while all of the rest had air source heat pumps. Now, in all cases, there were other fabric measures adopted alongside the heating systems, and I'm going to say a bit more about those in just a moment. As to cost, this is perhaps one of the more frightening aspects of the work, that the cost of upgrading in these ways, so both the heating systems and fabric measures, including all energy and maintenance costs over a 15-year period, which is the time frame we were asked to look at by Bayes, ranged between £9,000 at the low end for a small flat, up to nearly £27,000 for the sprawling detached home with solid walls. Now, the heating system is only part of the story, and I said there were other fabric measures that were adopted for each package in the cost optimal package in every case too. And this chart shows both sides of that equation. You can see for the first house type here, the small flat, that as well as the storage radiators that I spoke about, here we have air tightness improvements, and quite dramatic air tightness improvements, which reduce air change rates down to 0.5 air changes an hour, alongside additional top-up roof insulation. And you can see similar measures carried out in all of the homes. Notice that in most cases, almost all cases, it's the low-cost measures that are chosen, and high-cost measures like batteries, thermal stores, and floor insulation are actually never chosen among these cost optimal selections. The previous optimization I showed on charts was all using the time of use tariffs, which are a very competitive rate of tariffs. And depending what tariffs are used, whether you're on current ordinary flat rate tariffs or whether you're using time of use, that translates into different packages of measures. And you can see that I've marked two here, where the two larger homes with solid walls, when you switch between time of use to conventional tariffs, they change, and now, because of the increased energy costs per unit, external wall insulation is now justified in the cost optimal run. And because there is now external wall insulation, a smaller heat pump is also needed. And that in turn means that the heat pump, the most cost competitive heat pump, changes from being air-to-air heat pumps in the time of use tariffs to being a low temperature air source heat pump with radiators. And that's because the way the costs scale for air source heat pumps is differently from air-to-air. Now, those were just the cost optimal, a single choice for each of the house types. This chart shows you the cost optimal selection of measures for all heating types and all house types. You can see house types are shown here across the bottom, and heating types here shown vertically across the side. And again, you might want to choose your own house type and look at how these costs would flow through for you. But what you can see in most cases is that the low temperature air source heat pump is coming out with lowest cost. They're the ones that are marked with the black border in most cases, whereas the ground source heat pump with underfloor heating is coming out most expensive in all cases. There is no simple relationship between the baseline costs, so what you're currently paying for total costs over 15 years, and these baseline costs are energy costs only, but there's no simple relationship between those baseline costs and the costs after the upgrade package has been enacted. And you can see, for example, in the case of the ground floor flat, total costs over 15 years actually fall a little bit, whereas in other cases, like the mid-floor flat, you can see that total costs over 15 years rise very dramatically, a threefold increase in this case. So you can't generalize across cases the relationship between your baseline costs and the upgraded costs. And the other point I'd like to make here is that actually, on quite a number of occasions, the difference in cost from the first to second or third best or most cost-effective measures are very small. So, for example, for the bungalow, it's a difference of less than £1,000 between the first choice to the third choice. For the medium end of terrace with cavity walls, you can see again very small difference, less than £1,000 between the first and the third choice. So there are some baskets of measures that actually don't have significantly different costs. How does this flow through into energy consumption? And again, you can see perhaps your own baseline energy use here. For example, the mid-floor flat is 2,000 kilowatt hours a year of electricity, a bit over 6,000 kilowatt hours a year of gas. And in all cases, all electric heating systems result in less energy use overall, but many of them, quite predictably, are shifting gas to electricity. And the other important point is that from highest to lowest, there is typically a doubling of energy consumption, depending on which basket of cost-effective measures is chosen. Now, as well as the annual energy consumption figures, because we're doing these high-resolution runs at 10-minute intervals, we also know quite a lot about very detailed energy scenarios. And this was an example that Bayes asked us to look at the potential for flexibility for shifting power demand from one period to another with a whole series of different technologies. This one looks at batteries, and this high resolution data allows us to work out, this is a simple example, but it allows us to work out that if you have an 8 kilowatt battery in a sprawling detached home with cavity walls, you can anticipate savings of about 2,500 watts for a duration of a bit over 3 hours. This is a really useful piece of information when it comes to thinking about future flexibility we might be able to achieve by using electric heating. Now, from a climate change perspective, greenhouse gas emissions are the most important output. And the good news here is that emissions for almost every one of these new cases of electric heating are lower than the original emissions. And in many cases, they are less than half of the original emissions. You can see that the most efficient, or the lowest greenhouse gas emissions tend to come from the ground source heat pump options, which are sadly the most expensive ones, and there's a trade-off here. But remember, on this chart, we haven't optimized for emissions. We have been optimizing on each occasion for cost rather than emissions, and we're intending to do this in the future. Okay, I'm going to try to draw things together and draw out some conclusions now. The first point to make is that this prevailing wisdom of the way we should incorporate electric heating in homes is quite different from what we've found. And we think existing homes can be converted to electric heating at much lower costs than the accepted wisdom. So rather than spending maybe 70, maybe £100,000 per home, we can bring those costs down to only 10 or 15,000 pounds capex per home. The next point is that most of the fabric measures that are normally recommended for use with heat pumps aren't justified on purely economic grounds. There might be other good reasons for insulating, for the more expensive measures, to do with comfort or maybe humidity and condensation. Those other issues, but they wouldn't be justified on purely financial grounds. But the tricky thing here is that the trade-offs there are between higher capex, lower running costs, and the optimum carbon emissions per pound spent differ in very complicated ways that are difficult to foresee without looking in real detail at the individual home, and would be very difficult to understand without a model like this code model we've developed. If we try to scale up the work that we've done to consider the impact across the whole of the UK building stock, it would cost around £320 billion to switch all homes over to electric heating. And given that we have 30 years, that means spending £11 billion a year. That's a huge sum of money, clearly. And to try to put that into some kind of context, we're currently spending in the UK about £3 billion a year on refurbishment and maintenance. So in order to switch to electric heating, we need to factor that up by about 3.5 times, which is a stretch. But if government is able to put up some of that money, that is still possible. And if we're to do that, if we're to spend all that money and we're to go through those lengths to electrify homes, it means upgrading 900,000 homes a year in order to reach the 2050 target. And that in turn would require more than 4,500 skilled installers. That's a very simple scaling up of those figures, but that gives you a feel for the magnitude of change that's required, given that currently we only have a few hundred installers who are capable of installing heat pumps and electric heating. So to go back then to the question I posed in my title, will electrification mean that we're able to meet the UK's carbon emissions? The reality is that would certainly move us in the right direction, but that alone would not be sufficient. It would take more than that to be confident of meeting our climate change obligations. Thank you.